So Veritasium just dropped a new video, and as we know, Veritasium don't miss. That man just doesn't miss. No, he's good. He's fucking good. This guy Veritasium right here. Always making high quality content, you know. People have witnessed supernovae, kind of a weird term. I always call it supernova. I don't like the supernovae term, but whatever. What threat do they pose to life on Earth? I mean, I've already seen the universe is threatening to what is it? Fucking what's the word? Like hostile to computers because of particles and shit that come and fuck up the stuff inside of the stuff in your computer. Sure, if you guys have seen that video, you'll know what I'm talking about. But like, yeah, there's a lot of space stuff, particles and stuff that rain down everywhere and stuff. And you know, if a star explodes near the Earth, I'm guessing atmosphere problems, perhaps changes in a lot of stuff, temperature, cancer. You know, that's probably something that people might not think of at first, but I got a whole lot of cancer that I'm feeling. If there's like the sun, well, if the sun explodes, that's a whole different story. But you get what I'm saying.
What would happen if a star exploded near the Earth?
Tell us.
Well,
Damn.
The nearest star to Earth, of course, is the sun, and it is not going to explode. But if it had 8 times the mass, then it would go supernova at the end of its life. So what would that look like? Well, as noted by XKCD, if you held up a hydrogen bomb right to your eyeball and detonated it, that explosion would still be 1 billion times less bright than watching the sun go supernova from Earth.
From Earth? Damn.
That's how insane.
Why do stars have to get to a certain size to explode? Like, do the other ones not have enough energy to, like, combust? Weird words. I don't know this stuff. But, like, why do only the really big ones get to explode? The other ones, I know what they kind of do. They just kind of dull out. They become white dwarves and stuff like that. But, like, wait, actually, no, that also happens after a supernova, doesn't it? No.
Insanely powerful
You know what? I'll let
supernova
him explain.
explosions are. They are the biggest explosions in the universe. When we see supernovae in other galaxies, they are brighter than the combined light of hundreds of billions of stars. So bright, in fact, that they appear to come out of nowhere. On the 8th of October 1604, the astronomer Johannes Kepler looked up into the night sky and noticed a bright star he had never seen before. It was brighter than all the other stars in the sky, and about as bright as the planet Jupiter. On moonless nights, it was bright enough to cast a shadow.
Man, this is not the fucking sky I see, man. All this goddamn light pollution from cities. I wish I could see this night sky. I have to go out to, like, the wilderness and stuff. And how can you see Jupiter? Like, where do I look for the Jupiter at?
Kepler published his observations of this star in a book called De Stella Nova, which means about a new star in Latin. Kepler thought he was witnessing the birth of a new star, but it was actually a star's violent death.
Damn.
Over the following year and a half, the light faded until it was no longer visible. But the name stuck. Even once we learned what was really happening in the 1930s, the violent final explosion for stars between about 8 and 30 solar masses has been called supernova.
Nova, word for new.
But how exactly a star explodes is not what most people think. For most of a star's life, it exists in a stable balance. In its core, it fuses lighter elements together to make heavier ones, and in the process, it converts a small amount of matter into energy. This energy is really what keeps the star from collapsing in on itself. Gravity compresses the star, but that force is counteracted by the pressure generated by the movement of particles inside the star, and by the pressure of photons released by fusion. So, in effect, stars are propped up by their own light.
So it's keeping itself from collapsing.
If the rate of fusion drops at the center of the star, the temperature and the pressure decrease. Gravity starts winning, compressing the star. But this increases the temperature and pressure in the core, which increases the rate of fusion. It's a stable, self-regulating system.
Okay.
But there's a problem. Stars have a finite amount of fuel, which over time gets used up. Our sun is about 5 billion years into its 10 billion year lifespan.
That's a whole lot of fuel, though.
There are stars dozens of times more massive than the sun, which you would think would live much longer. But they actually use up their nuclear fuel faster.
I mean, this kind of makes sense. It's like, think of it in terms of engines. I know it might be a bad comparison, but you could say the sun, even though it's pretty big, you could say that's like a 4-cylinder, and then think of the bigger ones as being like, oh, it's a V8, it's a V12, right? With those cars, when you have those kinds of engines, they take up fucking gas. Okay, they will eat the fuck out of your gas, especially with these gas prices. If you have one of those V8, V12s, I mean, you're just suffering, But maybe you're not, because if you're buying V8s, V12s, you should know that you're going to be in a stable, situation where you can afford to keep having said V8, V12, because otherwise you're kind of fucked.
A star 20 times the mass of our sun
it makes
has
sense
a lifespan
that
of just
they would use up more
10
energy.
million years. And more massive stars burn hotter and even brighter, but for much shorter lives.
Much more intensity.
90% the life of a star, the core is only hot enough to fuse hydrogen into helium. And when the hydrogen runs out, fusion slows, gravity compresses the core, and its temperature increases to 200 million degrees, at which point helium fuses into carbon. There's enough helium to power the star for around 1 million years, but as the helium runs out, the core is again compressed and heated. Carbon starts fusing into neon, which lasts about 1,000 years, and then neon fuses into oxygen for a few more years, then oxygen to silicon for a few months, and at 2.5 billion degrees, silicon fuses into nickel, which decays into iron. Now, at the heart of this giant star, there is an iron core building that's...
Did he say much? That's like nothing in terms of this time. So I know that, all of the elements and stuff were created and all made in the bellies of stars, right? We're made of star stuff, as Neil deGrasse Tyson likes to say. And all of that was created and compressed within the bellies of these stars while they're doing their processes and stuff. So would that mean that a star would have to survive long enough? And the longer you go, the more elements that can be created and produced within here. So it's all about the longevity. So if you reach a longer state, you would just keep going up and creating these heavier elements, I'm guessing? So you could just keep on going and going and going and going. And you could keep that going for a long-ass time as long as you have sufficient fuel to do it. It's just that no star has ever had enough fuel to create more elements than we have recognized and acknowledged and we've put on that periodic table. Am I somewhere in the vicinity there? I don't know, man. This ain't always my cup of tea. I know a little bit, but not that much.
Few thousand kilometers across.
What if we could keep it alive and create more
stops.
Elements?
Instead of liberating energy as it fuses into heavier elements, it actually requires energy. Iron is the most stable element, so it actually takes energy both to fuse it into heavier elements and to break it down into lighter ones. Both fusion and fission reactions ultimately end up at iron. The iron core grows, but the crush of gravity becomes greater and greater as the rate of fusion drops. When the iron core is about 1.4 times the mass of our sun, which is known as the Chandrasekhar limit, the pull of gravity is so strong that something totally wild happens. Quantum mechanics takes over.
Oh shit.
Electrons run out of room to move and they're forced into their lowest energy states. They then become absorbed by the protons in the nucleus. In this process, the protons turn into neutrons and release neutrinos. With the electrons gone, the core collapses, and fast, at about 25% the speed of light. So what used to be a ball of iron 3,000 kilometers in diameter becomes a ball of neutrons just 30 kilometers across. Essentially, it's a neutron star. With no outward pressure to hold it up, the rest of the star caves in, also falling at a quarter the speed of light. It hits the neutron star and bounces off, creating a huge pressure wave. But this kinetic energy isn't quite enough to start a supernova explosion. No, the thing that really kicks it off is the humble neutrino. Now, I normally think of neutrinos as particles that do basically nothing. I mean, they interact so rarely with matter that right now, there are 100 trillion neutrinos passing through your body per second. It would take a light year of lead just to give you a 50-50 chance of stopping a neutrino. And that's because they interact only through gravity and the weak force. But in a supernova, when the electrons are captured by the protons, an unbelievable number of neutrinos is released, around 10 to the 58.
That's a big number.
You would think they would just fly off at nearly the speed of light, but the core of a supernova is incredibly dense, about 10 trillion times more dense than lead. And as a result, it traps some of those neutrinos and captures their energy. And this is what makes a star go supernova. A particle that is millions of times less massive than an electron, that barely interacts with anything, is responsible for some of the largest explosions in the universe. In that explosion,
they're the dark horse. It's like you know they're like the hidden gem. So how does it's just crazy, doesn't it? Like when you can't add trying to make sense to it because it's not really gonna make sense. In what way could this make sense to our minds that are only built for like socializing and stuff like that? But like it's just so strange and oddly beautiful, right? To like find out about this stuff and find out about it through obviously the medium of language, which is the thing that we created. But it's like it's just beautiful, man. It's just
only 1/100 of 1% of the energy is released as electromagnetic radiation, the light that we can see. Even then, supernovae have enough energy to outshine a whole galaxy. About 1% of the energy is released as the kinetic energy of the exploding matter, but the vast majority of the energy is released in the form of neutrinos. And neutrinos are actually the first signal we detect from supernovae. And that's because after they're generated in the core, they can escape before the shockwave reaches the surface, where the light that we see is generated. So neutrinos can arrive on Earth hours before the photons, giving astronomers a chance to aim their telescopes at the right part of the sky.
That's useful.
I actually used to work at a neutrino observatory back in college, and I would work the graveyard shift between midnight and 8 a.m. So if I detected a really big increase in the neutrino flux during my shift, it was my job to call and wake up scientists so they could go look out for a supernova. Now that never actually happened, but we did have some close calls. Now I need to clarify a couple things. First, not all really massive stars explode.
Okay.
As they collapse, some form black holes instead, which means they do not go supernova. And second, there's another way to make a supernova. Sometimes a white dwarf star, which is incredibly dense, pulls matter off a nearby star. And when its mass reaches that Chandrasekhar limit of 1.4 solar masses, the white dwarf collapses, creating a supernova. This is actually the type of supernova that Kepler saw in 1604. A supernova 20,000 light years from Earth.
How the fuck would we know that?
Now, because the shocks are asymmetric, supernova explain neutron stars that can move really fast. There's a neutron star we've observed with a velocity of 1,600 kilometers per second. And we think that was caused by a very asymmetric supernova explosion, sent it shooting off in the other direction. Despite only recently learning about how supernovae work, humans have been observing them for thousands of years. Ancient Indian, Chinese, Arabic, and European astronomers all observed supernovae. But they are quite rare. In a galaxy like our Milky Way, consisting of 100 billion stars, there are only about 1 or 2 supernovae per century. A particularly amazing example is the supernova of 1054, when the light of a supernova 6,500 light years away reached the Earth and was recorded by Chinese astronomers. If we look to where that supernova was recorded, we see the Crab Nebula. It is a giant remnant of radioactive matter left behind by the explosion. In the 1,000 years since the explosion, the remnant has grown to 11 light years in diameter. Supernovas produce a lot of cosmic rays. Cosmic rays are actually particles, mainly protons and helium nuclei, and they travel out.
What are we a part of, man? Like, what even is all of this happening? What even is this that we're observing? Like, what really is it? Are we missing some sense because our senses are only built to protect us from wildlife and dangerous situations? Like, we only have the senses that we needed to develop through evolution, and that's what they'll tell you, right? Like, is there another set? Like what is this that I'm seeing? Like, what even is what is going on out there? How does any of that exist? And no, I am not fine with just simply saying, oh, clearly it must have been created. That's like, we're susceptible to just simply always going down that path of thinking that there's some kind of cosmic creator and stuff like that. But really, who am I to say what it is? I don't know. It seems like unlikely that this could ever be created. Like, it just seems so odd and rare, and it's so marvelous. It's miraculous, really. It's just crazy. Like, look at this. This is the cosmos. This is where we come from, right? I mean, that's what they say. But, I mean, they say is scientists that can back up their claims. Like, oh my God.
Very, very nearly the speed of light. Have a tremendous amount of energy. So, at what distance could a supernova cause problems for life on Earth?
Not
the
very
closest
far.
stars to us, besides the Sun, are the 3 stars in Alpha Centauri. They are 4.4 light years away. But stars do move around, and on average, a star gets within 1 light year of Earth every 500,000 years. So what would happen if such a star went off?
Yeah, so within a light year, you're easily within a danger distance from just the kinetic energy. So I think even at that distance, you're looking at possibly blowing the atmosphere off.
I got that
but
one.
We would also have other problems to worry about. Supernovae create conditions that are hot enough to fuse elements heavier than iron. In the months after the explosion, these elements undergo radioactive decay, producing gamma rays and cosmic rays. Less than 0.1% of the energy produced by a supernova is emitted as gamma rays from these radioactive decays, but even this tiny percentage can be dangerous. At a few light years from a supernova, the radiation could be deadly, though most of it would be blocked by our atmosphere. Now, the Earth is protected from solar and cosmic radiation by our atmosphere, and specifically by ozone molecules, 3 oxygen atoms bonded together. But high-energy cosmic rays from supernovae can come down and break apart nitrogen molecules in the atmosphere. And then these bond with oxygen atoms, which can then break apart ozone. And so we can lose a lot of our ozone if there's too many cosmic rays coming from supernova events, and that can expose us to all kinds of dangerous radiation coming in from space. We actually see an increase in atmospheric NO3 concentrations coinciding with supernova explosions. A supernova within 30 light years is rare, only happening maybe once every 1.5 billion years or so. But a recent article suggests supernovae could be lethal all the way out to 150 light years away, and so those would be much more common. We actually have evidence for a supernova that went off 150 light years from Earth 2.6 million years ago.
Well, most of the stuff this one I was going to mention is most of the stuff that we're watching. We watch a supernova that's super far away based on the way that stuff works, like time. Then that supernova is not actually really happening in the present moment as we're experiencing it, right? Technically, it's happening 2.6 billion years ago, but really, that's also not really what's happening. It's not like it really happened 2.6 billion years ago, is it really?
Seen by our early human ancestors like Australopithecus. And we know this because there are elements present on Earth that could only have been deposited by a recent supernova. In sedimentary rocks at the bottom of the Pacific Ocean, scientists have found traces of iron-60 in a layer that was deposited 2.6 million years ago. Iron-60 is an isotope of iron with 4 more neutrons than the most common type of iron. Iron-60 is really hard to make. Our sun doesn't make it, nor is it produced basically anywhere else in the solar system. Iron-60 is made basically exclusively in supernova explosions. And iron-60 is radioactive. It has a half-life of 2.6 million years. So every 2.6 million years, half of the sample decays into cobalt-60. So all of the iron-60 that was around during the formation of the Earth 4.5 billion years ago has definitely decayed. So the iron-60 that the scientists measure is proof of a recent supernova. Scientists also measured trace amounts of manganese-53 in the same sediments, giving further evidence supporting the idea that recently there was an explosion of a nearby supernova. The supernova that happened 2.6 million years ago wasn't catastrophic for our ancestors, but some researchers hypothesize that it could be related to the mass extinction which is seen at the Pliocene-Pleistocene boundary in the fossil record around the same time.
Who's naming this?
This extinction wiped out around a third of marine megafauna. The idea is that the cosmic rays from the supernova hit particles in our atmosphere, creating muons, which are charged particles like the electron, only more than 200 times heavier. The muon flux for years after the supernova would have been 150 times higher than normal. And the bigger the animal, the larger the radiation dose it would have received from these muons, which is why megafauna were so disproportionately affected. And what's more, the animals that lived in shallower waters were more likely to become extinct compared to the ones that lived at depth,
you lucky
where
motherfuckers.
The water would have protected them from muons. Further evidence for these recent nearby supernovae comes from our place in the galaxy.
Man, those motherfuckers deep underwater though, oh, it's so like dark, and it's just, imagine being those animals down there. What do they think about? They don't think really, but well, they kind of do. Not really. They only think about eating and those basic animal instincts. It's just life trying to get away from death, because life doesn't necessarily need to have the capabilities of reasoning and conscious thought like we do. Or does it? Because according to evolution, this could have just come out of simply just usefulness for us, you know, because we're obviously social animals. Those guys down there, they must not be that much social, but just imagine being like something that is down there in those depths. It's so dark. It just feels so lonely, and like, it just feels like hell. Like, I wouldn't want to be that animal. Like, I feel like I deadass wouldn't want to be that animal. It's fucking scary down there.
You know, if you look in the space between the stars in our galaxy, on average there are around 1 million hydrogen atoms per cubic meter. That may sound like a lot, but it's basically a perfect vacuum. But for hundreds of light years in all directions around our solar system, you find there are 1,000 times fewer hydrogen atoms. It's like they've all been blown out somewhere, and our solar system is existing in this cosmic void inside a low-density bubble. So that is evidence for maybe tens of supernovae that would have blown all this material outwards. But there are cosmic explosions that are even more deadly than normal supernovae: gamma-ray bursts. Gamma-ray bursts were discovered by the Vela satellites, which were looking for Soviet nuclear tests. But on the 2nd of July, 1967, the satellites detected a large burst of gamma rays which were coming from space. There are two main sources of gamma-ray bursts: mergers of neutron stars and the core collapses of gigantic stars called hypernovae. Hypernovae are caused by stars that are at least 30
Isn't a core collapsing of a ginormous star a supernova?
Solar masses and rapidly spinning. Their collapse leads to an explosion 10 times more powerful than a regular supernova, and it leaves behind a black hole. The gamma-ray bursts caused by hypernovae channel most of their energy into beams which are just a few degrees across.
It's like you're spitting
if there was
fire.
A gamma-ray burst within 6,000 light years, it would decrease the ozone level enough that it could be catastrophic. To put this distance in context, a sphere with a radius of 6,000 light years contains hundreds of millions of stars. On October 9th, 2022, astronomers detected one of the most powerful gamma-ray bursts ever measured. It was powerful enough to measurably affect how the ionosphere bounces radio waves. The effect on the ionosphere was around the same as a solar flare. But this gamma-ray burst was located in a galaxy 2.5 billion light-years away.
Jesus.
Astronomers speculate that a gamma-ray burst could have caused the late Ordovician mass extinction, which wiped out 85% of marine species 440 million years ago. There is no direct evidence, but gamma-ray bursts are common enough that it is estimated that there's been a 50% chance that there was an ozone-removing, extinction-causing GRB in the vicinity of Earth in the last 500 million years. So, if a supernova or a gamma-ray burst were to go off near the Earth now, that would be pretty catastrophic. But in an ironic twist, we kind of owe our existence to these sorts of explosions. Because 4.6 billion years ago, it was probably the shockwave from a nearby supernova which triggered the collapse of a cloud of gas and dust that gradually coalesced to form our solar system.
Yeah, that's how things work.
So the sun, the earth, and all of us wouldn't be here today without the explosion.
Those molecular gas clouds colliding into a star. And boom, in the bellies of those stars, you have a machinery. It's a factory for heavier and heavier elements. That then when the explosion comes, boom, you spit them out. Boom, 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 spit them out, spit them out. Just putting that out there. That's the product. We are the product.
Explosions of nearby stars.
Man. Beautiful video, Veritasium. Loved it. What happens if a star explodes near the Earth? Probably not nothing so great, you know. Where we're in I'm surprised because, you know, 6,000. No, is that 6,000 light years? Did he say 6,000 or 600 or 6? No, he said 6,000 for the gamma rays. And that has hundreds of millions of stars. That's a high number. And the likelihood of any of them having one of those, is that supposed to be that rare? With 100 million? Well, when you have a pool of 100 million, it's kind of rare for anything to be rare that happening in those things with that much numbers of things. Phew. I mean, look, man, there's a lot of volatility out there, man. It's just explosions. It's like, what is it? How is that a thing? What caused any of this, man? Will we ever know? Is there anything to be known, right? Because you say, will I ever know? Well, also, will I ever know what? What if there is no origin story? This is just what it is. It is what it is. And we create this concept of origin and it having to come from somewhere or someone, right? That's what I've always thought. I've always thought it doesn't make any sense. You know, obviously I can't make sense of it. I'm not built to make sense of it. I'm not designed in the way that I'm not designed to, you know, figure out the universe. I'm designed to get along with people in a tribe so I can survive long enough to reproduce. Right? Because if I'm in a tribe, there's a chance I won't die. Because alone, I might get eaten by a bear. But anyways, hopefully you guys enjoyed. Subscribe if you want. And let me know what you guys want me to react next. If you made it to the end, let me know. I will pin your comment and all of that good stuff. You're the GOAT. I appreciate you. For sure, for sure. Yes, sir.